How many people do you think can read your messages right now? Every time you send a message, make a payment, or log into your bank account, someone could be watching. Your online data travels through dozens of servers, cables, and routers owned by companies you have never heard of before reaching its destination. And yet, even if someone intercepts every single bit of your message, they can't read a single word. And it's all because of one idea that changed communication. Think back to passing notes in school. If your teacher intercepted your note, she could read it instantly, which most of the time meant game over. Unless you and your friend had a secret agreement beforehand. For example, shift every letter 3 spots forward. With that, the letter A becomes D, B becomes E, and car becomes FDU. This is the foundation of encryption. It's the process of turning readable information into unreadable noise, unless you have the right key. The idea is actually ancient, and it was used by Julius Caesar to send military orders, which is why we still call it the Caesar Cipher. But this method has an obvious problem. Anybody can easily crack the encrypted message by just trying every possible shift until the message makes sense. There are only 26 letters in the English alphabet, which means you would only need to try at most 26 keys, and that takes only seconds. Now, instead of shifting every letter by the same amount, a better encryption idea would be to shift every letter by a different amount. So, let's take a random 8-digit key. Each digit shows how many positions each successive letter will be shifted to encrypt a longer message. Guessing the key would be a lot harder for a human, as with 8-digit encryption we get 100 million possible keys. But in the modern world, bad guys don't use a sheet of paper and a pencil anymore. They are armed with computers and data centers, allowing them to guess billions to trillions of combinations every second. That's why today's secure communications are encrypted using 256-bit keys with combinations so large that even a computer testing billions of combinations per second will need longer than the age of the universe to crack it. But now, we have a different problem. When the sender and the receiver share the same key to scramble and unscramble a message, we call it symmetric encryption. And with symmetric encryption, the secret key has to be agreed on before sending the message. But without meeting in person, how do we share a key without someone intercepting it? Yeah, we're right back where we started, because if we just share the key through the internet, someone will intercept and use it to decrypt our messages. But in the 1970s, right around the time the internet was being born, some of the greatest mathematical minds on earth solved the puzzle that had remained unbroken since the time of Julius Caesar. They realized that to secure communication, we had to stop using the same key for everything, so they invented asymmetric encryption. And the idea behind it is surprisingly simple. Instead of one shared key, we use two. A public key that can be shared with anybody so they can use it to create a secret message, and a private key that is not shared with anyone and only you can use it to decrypt the secret message. The two keys are mathematically linked as they are generated from two enormous prime numbers multiplied together, and the result becomes part of your public key. But reversing it by trying to figure out which two prime numbers were multiplied is computationally nearly impossible, even knowing the result. Now, when two strangers want to communicate securely over the internet, they just exchange public keys first. There is no secret binting required, and there is no risk of interception, because intercepting a public key is useless without a private key. So, if asymmetric encryption is so perfect, do we just use it for everything? All the time? Actually no, because there is a smarter solution. Instead of doing those massive prime number calculations all the time, we combine the best of both symmetric and asymmetric encryption. Every time you open your browser and navigate to a site, a silent two-step process happens in milliseconds. First, there is an asymmetric handshake, where your browser and the website trade public keys to establish a secure connection. And once they have the secure connection, they use it to pass a temporary symmetric key, switching to the ultra-fast 256-bit symmetric encryption. Basically, we use asymmetric encryption to share the key and symmetric encryption to pass the data. And this invisible process is happening billions of times every single second across the planet. It's what protects your data when you buy a coffee, check your bank account, or send a message on WhatsApp. Without it, the modern internet as we know it today simply couldn't exist. The answer to how many people can read your message is practically nobody, because intercepting encrypted data is useless without a key. But cybersecurity is only as strong as its weakest link. Encryption secures the pipeline, and you secure the endpoint. Don't let a lazy password ruin a brilliant piece of mathematical engineering. Head over to my videos on passwords right here to make sure your accounts are actually secure. This is Tech That Clicks. I'm Raoul, and I'll see you in the next one.